All right, ladies and gentlemen, good afternoon. Welcome to episode 16 of Fighting for a 5, where we go over the document problem number 17. Of course, brought to you by the great Couch Potato brand Snack Foods and Beverages. Thanks again to Kevin and Sean for the logo. I am your host, Mr. Geratino. All right, so this problem deals with a hypothesis test. And a few of you expressed some concern about how to choose the appropriate procedure. And I'm definitely going to spend time talking about that, focusing on that topic this week. But just a little sort of what goes through my mind when I'm trying to decide which procedure is the first thing I ask myself is, are we dealing with quantitative data or qualitative/categorical data? So we're analyzing, in this case, the chance of developing colon cancer. And the way we're doing that is we are taking 1,000 volunteers, we're randomly assigning them into one of two groups. And then basically by the end of some amount of time, in this case 6 years, we go back and we survey those 1,000 people and we ask them, did you develop colon cancer? So each individual will either be a yes or a no. In other words, each individual falls into a category. So this is categorical data. And I know that the way we analyze categorical or qualitative data is we study proportions, usually proportion of success. In this case, it happens to be that the proportion of success, or the proportion that we're interested in, is proportion of developing this type of cancer. So I know that just by doing a quick glance, we are going to be using some kind of a proportion Z test, right? So like one thing that will jump out when you're studying quantitative variables is the information that will be given to you will contain like means and standard deviations. If you see a mean and a standard deviation as part of like a summary statistic, then you know you're dealing with quantitative data, in which case you'd be using some kind of a t-test, right? That is not what's going on here. We have qualitative data, so we're going to use a z-test, specifically a two proportion z-test. Now, why two proportion z-test? Well, again, we have two separate groups going on here, okay? One of the groups will be people that take low-dose aspirin. Another group will be people that take some placebo, all right? Reading further, it says to use a significance level of 0.05, and we're asked the question, do the data provide convincing statistical evidence that taking low-dose aspirin each day would reduce the chance of developing colon cancer among all people similar to the volunteers? Now, this means we are running a hypothesis test, right? Because the question is not asking you to estimate the difference. It is simply asking you to determine if the information that we see, the observed information, provides evidence that indeed we do have some kind of a statistically significant result showing that aspirin actually reduces cases. That being said, of course, the very first step, I should always define my parameters. So in this case, I'm interested in two separate parameters: the true proportion of those who develop colon cancer while taking aspirin, and the true proportion of those who develop colon cancer while taking a placebo. And more specifically, we're actually interested in the difference between these two numbers. Of course, again, we're going to run a two proportion z-test. And in order to analyze the situation, we're going to make an assumption about these parameters. We're going to assume that they are exactly the same. And so that's my null hypothesis. Notice that my null hypothesis is defined in terms of the parameters and not the statistic, right? Because the parameter is some information about the population that we're interested in that we don't currently know. In fact, we may never know. We're gathering statistics to infer something about the population. The alternative will be that the difference PA minus P plus PL will be less than 0. Now, if you subtract in this order, you would have a less than alternative. If you subtract in the opposite order, you would have a greater than alternative hypothesis, and that's totally fine. Okay, you're allowed to subtract in either order as long as your alternate hypothesis sort of reflects that. All right. Again, the reason why this order will get a less than is we are trying to see if there's evidence that taking low dose aspirin would actually reduce the chance of developing colon cancer. So in theory, we're hoping that PA is going to be less than PL. All right, so two proportion z-test. Now we go, what I like to do is just list the observed statistics, and I call that P hat A, which was 15 over 500, and P hat PL was 26 over 500. So, I mean, what we're seeing here is that based on the statistics, there was a lower chance of obtaining or developing colon cancer if you took the aspirin in at least this group of 500 people, or a group of 1,000 people, I should say. Now that, of course, could just be sampling variability. So we must continue. Just because P hat A is less than P hat PL, we have not proven anything. We must see if this is a significant difference. All right. Now, in this situation, this is the hypothesis test where we use P hat pooled. P hat pooled is going to be our approximation for PA and PL, right? We're assuming that PA is equal to PL. That's what the null hypothesis is saying. But just because we're saying PA is equal to PL, that doesn't actually mean that we are making any assumption about the actual values of PA and PL. In fact, we have absolutely no idea what PA is in terms of a number. We don't know what P of PL is in terms of a number. So if we want to run our analysis, we need to approximate these values. And since we're assuming they're the same, we might as well pool our two small samples together to get one large sample. And this is going to be our best point estimate of PA and PL. So P hat pooled is the best point estimate of PA and PL. So wherever the parameters come into play throughout this analysis, we're going to use P hat pooled because that's our best estimate, right? And it turns out that the parameter comes into play, the parameter values come into play in a few different spots. First of all, they come into play in the success failure condition. So this is the first justification. We need to check this in all conditions for both samples. So the success failure condition is just, it's really officially n times p greater than 10 and n times q greater than 10. But again, we don't know what p is. We don't know what q is. So we're going to use our best estimate, and that would be P hat pooled and Q hat pooled. It's very clear for both of these samples that the success failure condition is met. There are such large sample sizes, and the probability of success is not an entirely small number. The 10% condition, so this is just asking, is our sample size less than 10% of the population? And yes, it's very clear that 500 is less than 10% of each of the populations. And the population in this case are like people that could potentially develop colon cancer. Actually, the way they describe it here is among all people similar to the volunteers. So I'm pretty sure that there are many people that are similar to the volunteers. So the 10% condition is definitely met for both of these samples. Random/representative, well, randomization was used to assign experimental units to the treatments, and therefore this condition is met for both samples. And then when we're dealing with two separate samples, we do need to make sure that the two treatment groups or the two groups that we're comparing are independent of each other, right? If they were dependent on each other, then it really doesn't do anything to help for us to compare the two groups. So we want to make sure that the two groups are independent. And I think it's pretty clear that the results from the aspirin group and the results from the placebo group are independent of one another. All right, so we've justified the conditions. And what this means is now we know what our sampling distribution will look like. In other words, we know what the p hat A minus p hat placebos would look like if we were to take many, many random samples based on our assumption that p hat, that PA and PPL are equal to one another. The sampling distribution would be centered at 0, and it would have a standard error of radical p hat q hat over n1 plus p hat 1 p hat 2 over n2. But actually, of course, we're not going to use p hat 1 and p hat 2. We're going to use our better estimate of each individual parameter, and that would be p hat pooled. So make sure we're using p hat pooled in the calculation of standard error. So that's already two places where p hat pooled comes up. P hat pooled comes up in the success failure condition. These are all p hat pooled and q hat pooled values. But then p hat pooled also comes up when you're doing your pq over n values for standard error. All right, so it turns out that this standard error ends up simplifying to approximately 0.0125. Great. Now we list our observed statistics. So what difference did we observe? It turns out that that was -11 over 500. And then we calculate our test stat. So test stat is always observed minus mean over standard error. And in this case, that's -0.022 over 0.0125, which is approximately -1.7542. So that's the z-score of the observed statistic based on our null hypothesis assumption. Then, of course, we get into the very important number, the p-value. This is really what's going to help us make our decision. So the p-value is simply what's the probability of observing our sample difference or less. The reason I'm saying or less is because that's what my alternate hypothesis says. Right, so I have to state my p-value so that it's consistent with HA. By the way, I forgot to mention that we're using an alpha value of 0.05. Maybe I did mention it, but I feel like I should mention it again because we're going to use it very soon. And by the way, they told us to use that value. Equivalently, we can also state this p-value as the probability that z is less than -1.7542. I don't care which one of these you use. You do not need to use both. It's fine to use both. I like using both, but you choose whichever one you'd like. They're exactly the same. It turns out that this probability is 0.0397, right? And of course, remember, this probability is based off of this sampling distribution, and that sampling distribution is based off of this assumption, right? So this probability completely follows from our null hypothesis. And so for my summary, I'm going to first interpret the p-value. This is not required unless they explicitly ask you to interpret the p-value, but I think this test is going to be one that really focuses on interpretations. And so I'm going to, every time a p-value comes up, I will interpret the p-value. Basically, the way you interpret a p-value is you say, if the true difference between proportion of aspirin takers who develop colon cancer and proportion of placebo takers who develop colon cancer is 0. In other words, this whole sentence is basically saying if H null is true, then the probability of observing a sample difference of -11/500 or less is 0.0397. Now notice that I chose the literal translation of this first probability statement. You could have actually also chosen to literally translate the z-score probability statement. Again, they're equivalent. I don't care which one you use. I like using the p hat A minus p hat placebo because it just helps me add context to the situation. All right, so that probability is 0.0397. Now on to the decision. Since that p-value is less than 0.05, which was our alpha value, we're going to reject H null. Right? Alpha is the thing that tells us what is considered rare. So in this case, alpha is 0.05. So anything less than 0.05 is considered rare. And when I say rare, it seems like it's too strange of a situation to have occurred. So either we got very lucky or something else is wrong, and that something else is that our null hypothesis is probably wrong. So that's why we decide to reject the null hypothesis, right? We either got really lucky or the null hypothesis is wrong. So we're going to say we reject H null. And moving on, let's finish off with some nice context in terms of the alternative hypothesis. So we say we have evidence to support the claim that taking low-dose aspirin would reduce the chances of colon cancer development. That last sentence is basically rewording their question. So they ask, do the data provide convincing statistical evidence that taking a low-dose aspirin each day would reduce the chance of developing colon cancer? And so I restated my alternative hypothesis statement to kind of sound like the way they asked the question. So we have evidence to support the claim that taking low-dose aspirin would reduce the chances of colon cancer development. All right, ladies and gentlemen, that is all for this video. I hope it helps, and I will see you again with the very next video for the very next problem. All right, take care. Bye.